My name is Ionuț Gîngu, and I'm going to talk about starter security practices for onboarding builders. A little bit about me. I started working with blockchain in 2022. I started doing security in 2023, and I've been a security researcher at OpenZeppelin for about 2 years now. OpenZeppelin is a security company which does traditional audits, both on-chain and infrastructure code. We also develop a lot of open source free tools for anyone to use, such as the OpenZeppelin libraries. I've been part in many audits since I joined. And then also in my research time, I've been studying a lot of bugs that happened outside the company or exploits that were popular. Sometimes I summarize some of those and we post them online. So if you want to read some of them, you can follow me on X. I let my handle there. I'm not very active, but if you have any messages for me, I will see them at some point. Okay. So getting into the agenda, I'm going to introduce the concept of the defensive developer mindset, what it is, and how you can introduce it in each phase of your product. Then I am going to have a slide with further resources that you can look into after the presentation if you're more curious about security. Then I'm going to leave a couple of minutes at the end for questions and answers. So, the defensive developer mindset, what is it? It's the process of allocating and spending time to increase security, not only to implement business logic. You are going there to develop your code, assuming things can go wrong, not assuming they are going to go through the happy path. What does it entail? So, for the implementation phase of your product, you'd want to reason about and ensure each line of code is secure by itself, like the actual code inside. And every function, you'd want to reason about it and the whole contract and the way it interacts. You'd want to have a testing phase where you want to quickly and automatically assert that code is correct. This not only prevents you from having bugs and makes you discover them early doing this kind of quality assurance work, but it also prevents regressions. So whenever you're going to make an update of the system, you'd want to assert that it still works correctly. And the ideal would be that you do that quickly and automatically rather than clicking something in remix all your functionality and being really error prone. Then you'd have your deployment phase. You'd want something that is predictable and robust and sets up through scripts. Again, this reduces human error. Most systems are pretty complicated nowadays. There are contracts that live behind proxies. You need to deploy them, initialize them, connect them with each other, set up some config variables, and again, you wouldn't want to do that in Remix. And then the operations phase. This is a phase basically where you maintain your system and run transactions on your blockchain, again with configurations. You're probably going to have some kind of ownership or permissioned entity that can make these important changes. So you'd want that ownership to be decentralized. You'd want to use something like a multisig, and then you also would want to make sure that whatever you're signing as part of the multisig is the intended data. And this is going to tie into some recent exploits that happened. So the implementation phase, how to get into the defensive developer mindset. You should build up this behavior of asking yourself a couple of security questions whenever you're coding anything. So I'm going to list here a couple of them. Simple questions. What are the entry points to my contract, and are they access controlled? By entry points, we mean any external or public function that can alter state and hence can provoke any change in your system. Can my code have any corner cases? Can users provide unexpected or malicious input or use my functions in a way that I didn't intend them for use? And then, am I handling all return values? Or are there any functions that return a Boolean, which I'm not treating, and in this case, my transaction might lose its functional atomicity, because I'm expecting it to do 3 steps. One of the steps doesn't work, and my transaction doesn't revert. So it only happens that 2 steps occurred, right? And then there's a couple of advanced questions you might want to ask yourself. In case of faults, can I pause the contracts? And would pausing cause further impact? There is actually projects where pausing is not really a good idea because you might be in a case where you need to act swiftly and withdraw some funds not pause the system while other things are ongoing at the same time, maybe declining prices. Does my system make economic sense? A simple example here would be if you're building some kind of lending, borrowing project, there is a bunch of design questions which you need to ask yourself, like how much collateral should people put in this project? What is the percentage? What happens if there is bad debt? What is the percentage or the probability that the system could actually go bankrupt? What would happen then? Is there any way in which I could limit damages in case of an exploit? Here, one simple thing that comes to my mind is the circuit breaker EIP. This is basically an authorized entity on your contract which could pause it. This authorized entity is governed by a private key, which is held by a bot. This bot is off-chain, periodically queries your contract for a key metric which you want to make sure is safe, right? And whenever a big spike in that metric happens, above a threshold you set, this bot acts and pauses the contract. Similarly, how in your house, when there is a high electricity spike or something, the safeties come down and your house is safe. And then lastly, can I fix my code if any bugs appear? So this ties into upgradability, or maybe if you don't have upgradable contracts, can I replace my contract with something else and then plug it back into my system to fix any bugs or issues that happen? Here I put a simple example of the can users provide unexpected and malicious input. We have a really simple contract. You can deposit any token inside and it's going to get tracked in this balances mapping. And then we have a simple function called swap tokens. Through this function, you specify a source token, a DEX, and some data, and the contract is going to take your balance, approve it to the DEX, and then call the DEX, presumably to make a swap for a target token and send it back to you. This is really good and safe if people use it for what you intended it to be used. However, this is actually a really common vulnerability where an attacker can specify an arbitrary address and an arbitrary call data. So instead of calling a DEX, they could specify the DEX to be an ERC20 token and the data to be a transfer from. What would happen then is that the contract would do a transfer from on the token, with itself being the message sender, so it would be authorized, and you would be able to drain any ERC20 token that is within this contract. It might seem a bit like a silly example, but this is actually really, really common. I've seen it more than 10 times, probably, in audits, in reports, and in exploits for a lot of money, this pattern. Okay, secondly, what you'd want to do in the implementation phase is to try to use battle-tested code. There are common functionalities where there's no need for you to reinvent the wheel. There are existing contracts which have been thoughtfully designed and are more secure by default because these popular libraries have been used and have been heavily audited. Not only they are more secure, but they also reduce your development time because instead of spending time implementing ERC20 transfer functionality, you can just focus on the custom logic that your project has. And here I wanted to give two examples. You have the OpenZeppelin contract libraries. This is the most popular library. It's been heavily audited and used in contracts for about 4 billion transactions. It has a lot of functionality such as permissions, proposals, voting, token standards, proxies, a lot of things, and it's in many environments, not only Solidity. And then there is another pretty popular option, Soulmate. This is a more experimental, gas-optimized Solidity library that heavily uses assembly. It's less battle-tested, and as I said, it's still in an experimental phase. It's becoming a bit more popular, but I would say treat it with a bit more care if you want to use it. Here I'm giving a simple example. This is a UI tool we have. It's a browser IDE where you can play with contracts and play with the libraries. So basically you select whatever token you want, and then you select what features you want, and it just combines them all together. In this example, I just put a really simple token with 1,000 pre-mint. I want it to be mintable and burnable, so this adds public functionality to mint and burn the tokens. I want it to be access controlled through roles, and I want it to live behind the transparent upgradable proxy. So this is all put together. You copy-paste this into VS Code, and then you're good to go. Moving into the testing phase. As I was saying, you'd want to have a way to quickly and automatically test your functionality in a robust way also. The first and simplest thing that comes to my mind is unit and integration testing. Unit testing is when you take one of your functions, separate it, you give it an input, you expect a particular output. And then integration testing would be taking multiple functions together or your whole contract. There are a bunch of frameworks that you can use to do these things. One is Foundry Forge, very popular. You can code in Solidity. The other one is Hardhat. You can code in TypeScript. Here I put a simple example of an integration test. I grant Bob the minter role for my ERC20 token. I assert that Bob has that role. And then I mint 1,000 tokens to Alice, and I assert that Alice indeed has a balance of 1,000. This would be a simple integration test. A little bit more advanced technique would be the fuzz and invariant testing. Fuzz testing is something that, again, you could do with the help of frameworks. Instead of having just a simple test with one input and one output, the frameworks run your test multiple times with many arbitrary inputs and assert every time that the output is correct. This also ties into invariant testing, which is a way to test key invariants or key mathematical properties of your system. So a simple example for what an invariant would be, you have an ERC20 token, you know that the balance of each holder summed up should always equal the total supply of the token. This is an invariant that should never be broken, and that's what you want to test. So here, I have a simple example. Again, you can use Foundry Forge, or there's Echidna and Medusa, two other fuzzing tools from a company called Trail of Bits. I have a simple example here. And what would happen if I plug this into the fuzzing and invariant testing framework? The framework would call all the functions on my ERC20 token in an arbitrary order with arbitrary parameters, minting, transferring from one to the other, and so on, an arbitrary number of times. And then at some point, it's going to check the invariant. Let's sum up the balance of each user. Is it equal to the total supply? If it isn't, it's going to error out, it's going to stop, and it's going to show me a trace of all the steps it did such that it reached this inconsistent state. So then I can run it back and figure out where the bug is. A last step you could do in testing is blockchain fork testing. So everything that I specified before was kind of assuming you have like a local simulated node, you run like a deployment on it, your tests, but it's kind of like this fake environment. What you can do is, again with some frameworks, you can fork the blockchain, make a copy of the actual node, the actual state that is right now on Ethereum, and you run your deployments and tests against that. But it's against a simulated real thing, not actually in production, so you're not spending gas. This is really good because it mimics the production environment and it lets you test things in a more real way. So imagine you have some kind of DeFi protocol which does a mathematical calculation based on Uniswap liquidity. There's two ways you can go about testing it. You can either mock the Uniswap pool and assume it has 1,000 ETH or 1,000 ERC20 tokens, or you can fork the blockchain and actually point your testing contracts towards a copy of the actual Uniswap pool, which has the real liquidity and it's like the real life conditions of it. Lastly, what you'd want to do in the testing phase is audits. So you'd want to hire some security professionals to do a line-by-line review of our code, as well as test it or help with overall design. After these reports come out of the audits, you would implement the fixes and then you would validate it with audit teams. So there's two ways to go about it. There's the traditional audits, and here is companies like OpenZeppelin or Trail of Bits. And there is this crowdsourced audits way, which is platforms like Sherlock or Code Arena. These are basically websites where you can go, you post a kind of a bounty. I say, I give $50,000 for a contest. Anyone can come and analyze my code. There's going to be a judging period, and depending on how many vulnerabilities each participant found, they're going to receive a percentage of that pot. Moving on into deployment, I was talking about wanting to have a quick, automated, and robust way to deploy your system that would be easy and consistent. This is most useful for big systems where you don't want to set it up manually because you can cause errors. Ideally, you would want your deployment to be atomic, which means you'd want it to happen within one transaction. There are systems that have certain marketplaces that tie together. So if you first deploy the marketplace without setting it up, and there is a time in which someone can act on that marketplace, they can actually steal all the funds, and this has happened before. So ideally, you'd have like a kind of a contract that ties up all your deployment, and you call that contract, and it deploys everything atomically in one transaction. So there's no place where anyone could put some, like make a transaction of their own and act on an inconsistent deployment. Then having deployment scripts would also make your deployment be more flexible. You would have some configuration files where you can just make some small changes, rerun the scripts, everything gets deployed fresh or gets upgraded if your system is upgradable. And then going into the operations phase. Who is the owner, permissioned entity of your system? So most systems have some kind of owner that sets, either upgrades a proxy, sets some operational variables. Basically, they have a lot of access, and if you compromise that, you probably can steal everything, right? So it's really important that that owner is protected by something. And here are multiple levels of security you could go for. There is the low security one. The owner is a private key. The private key is just one. It's easy to compromise through social engineering, as we'll see a bit further. Then there is maybe a medium security one, where the owner of your contract is a multisig. It has 7 people that could sign it, so whenever more than 4 of them sign off on a particular transaction, it's going to execute. In this case, you need to compromise at least 4 private keys. And then maybe a high security system. Your upgrades and all your operational configuration is managed through proposals that the community can vote on. Any proposal that passed would be behind the time lock that gives time for people who don't agree with it to withdraw from the protocol. And then you'd also have an emergency council of 3 out of 5 people that can instantly run any upgrade in case anything really bad happens. You have these trusted people that they can kind of bypass all these protections. But again, you're going to run into a similar problem as above, 3 out of 5. So people could compromise those 3 signatures. Lastly, about operations, how are you signing the transactions? Ideally, you'd want to use a hardware wallet because that is cold, it's not connected to the internet, and this is the safest and best practice accepted by everyone in blockchain. The problem is there are multiple steps where you can get tricked to sign something else. So if you think about the process of signing, you're probably in your browser on a Gnosis Safe UI. You put some information there that you want to sign. It gets hashed. You get this string of bytes. Those bytes go to your laptop, then to your hardware wallet. It gets signed, and then it goes all the way back to the laptop, to the Gnosis Safe, and on the blockchain. Here is a bunch of points that can be compromised to make you sign something else than you intended to. And I linked 3 really big hacks that happened, and this was the main cause. So this was about $1.7 billion. Somewhere along this line, all of these 3 projects were convinced to sign something else, either through malware that were showing them a different Gnosis Safe UI. So they were saying, okay, you're signing some kind of operational change, but under the hood, they were actually signing a transfer of ownership, and they didn't know. Or maybe on the laptop, there could have been, again, a malicious thing that intercepted whatever the hash was from the Gnosis Safe, change it. So when you're signing with the hardware wallet, if you're not checking that it matches the thing on the Gnosis Safe UI, again, you're signing a transfer of ownership. And that's exactly what happened in all the cases here. Then I just wanted to talk a bit about these safe utils. This is a tool that you can access online for free. It was made by an independent security researcher, and then some of my colleagues put it in a nice UI. You basically go there, you put your multi-sig address, the target of your transaction, the data, the nonce, and the value, and it's going to compute the EIP 721 thing for you, and it's going to show you exactly what you're supposed to see in Gnosis Safe and also on your hardware wallet, so you can check against that. A couple of further resources to look into if you're interested. So I put a bunch of resources for secure development. There's the Secure Smart Contract Development Roadmap, which is a more detailed resource about everything I talked about today, and then some links to Open Zeppelin contracts libraries and Soulmate, and then a couple of links about learning security. So the Solidity security documentation, then there is the Ethernaut Capture the Flag. These are a collection of about 30 security challenges that you could do for free, and each one of them highlights a certain security aspect we usually think about when we audit smart contracts. You could treat it as like a fun puzzle to do in a break. And if you can't figure it out, the solutions are online. And then consensus security best practices, and then vulnerable DeFi. It's another CTF related to DeFi. So thank you very much for listening. We can have some questions and answers now.
Oh, we already checked Ionuț. There's so many of them. And thank you so much for running us through contract security and everything. So let's turn over to the questions. So we have a few coming up here. So as you see on the top, we have... Did one just disappear? Why should I know all these as a developer if my code gets audited anyways?
Yes. So the reason why this is important and you can't just offload all the responsibility on the auditors is because it's really important that you understand security also. First of all, this makes your code be a lot better. So this reduces the costs you would spend whenever you come for an audit, because estimations take into consideration what things you are including as dependencies, what is the quality of your code. We look at all of those to estimate how much it's going to take to audit it properly. Secondly, if you understand some security, it's going to make you ask yourself questions where you end up understanding your system a lot better. So this has a bunch of really good implications. If you understand your system really well, you can prevent vulnerabilities before coming to an audit. Secondly, you can have a much better and swifter response in case of something happening. So if you don't really understand what's happening in your contract security-wise, maybe it's some complicated DeFi thing, if any exploit or bug happens, you're not going to be able to react really well and in a swift manner.
Well, thank you for that short answer.
And maybe just one other thing to add is that, especially with the testing, which I mentioned, so a lot of bugs that we find during audits are actually more like quality assurance things that could have been found through testing. So if the code comes to an audit and it's really, really solid in terms of the behavior you envisioned, that allows auditors to spend more time thinking about exploits rather than figuring out that your system is not even working in the way you intended it to work. That's something you can catch with a test.
Perfect. We actually have two that came in from Zero Knowledge. I think it fits perfectly into everything, right? So you mentioned Soulmate, but not Soulady.
Yes, so that's another experimental library. I didn't mention it because my impression is that Soulady is a library where it's like precursor work that's going to get into Soulmate. So yeah, they're kind of similar thing where they make experiments in Soulady, and then if it's good, they push it into Soulmate, or at least that's my understanding of it. But that's another library, yes.
So short and sweet. So we also have one more formula. I know test and test fuss, function names automatically picked up by Foundry. Is test integration also taken?
This is a very specific question, and I wouldn't know to answer right off the bat. My example with test integration was more like a general example. I didn't actually plug those into Forge or Hardhat to run them, but it was just like a generic concept. You can just look at the documentation and see which word you need to put there so it actually understands it.
So that just came in here. I think that was the one we missed before. Wouldn't introducing a circuit breaker introduce a new DOS attack vector?
Yes, it could do that. So my mentioning of the circuit breaker was more as an example of things you should reason about and think about whenever you're designing your system. It wasn't necessarily an endorsement of the circuit breaker technology. I would say it depends on a case-by-case basis. It's not a simple answer, a yes or no.
It never is. Those attacks are like, let's bring down Google. So anybody from the audience have any questions before we break for lunch? So I want to remind everybody before we go, there is a gym session here on the first floor in the terrace. Please, everybody go out and enjoy a good stretch. And I know everybody was going to sit and laugh in here. I don't know why. But thank you so much, Ionuț. And thank you for everyone. Please, everybody, give him a great hand.
Thank you.